Hello dear students, welcome to the lecture series on VLSI lab. Now this is VLSI lab number 7 from part B, and we are going to extend the lab number 7 what we have done in the previous lab. Now this lab we are going to call it as lab 7B. So basically we are going to understand the extended version of the common source amplifier. Basically we are going to understand how exactly the common source amplifier can be constructed in other way. That is, today we are going to see what are the other versions of common source amplifier. Specifically, we are going to change the load. So in the last lecture we have seen that the load was attached with the help of a diode connected PMOS. Now here in today's lecture we are going to see how this diode connected load can be removed, and we can attach one more efficient and effective load, which we call it as a current source or current mirror load. So how to perform that particular experiment and how exactly the schematic looks, we are going to perform the things. Now one common thing that will be there is this spice code. It is not going to change, it will remain as it is. The only thing is this portion, load portion, is going to change. So for that what I will do, I will try to create a new cell with the name common source current mirror experiment and say okay. So here is my big thing is created. So what I am going to do is I am going to just copy paste the entire thing what we have done in the previous class along with the spice code, because I will be requiring some common features. So I will just zoom it. Fine. Now spice code anyhow it is going to remain same, there is no change in it because it is a same common source amplifier we are dealing. But what exactly it is going to change here is the load. Now here the load was the diode connected PMOS. Now what I am going to do is I am going to remove this diode connected load and I am going to build the current mirror. So how to draw the current mirror? So we know that the current mirror circuit looks something like this. So let me extend this. Yes. So given a MOSFET, now current mirror can be drawn using either PMOS or NMOS. Now I am going to draw the current mirror or current source. I am going to tell what exactly the difference. So this is basically your current source, and what exactly it is going to do over here, the current whatever that is flowing over here, the current that is flowing over here will be exactly replicated onto this. Why it is going to replicate? Because as you can see, this is in the diode form, and the moment I connect it in the diode connected form, this device will be in the saturation region, and that means a constant current will be flowing in this MOSFET P1. And since the gates of both are tied together, which means the voltage drop across VGS of P2 will remain same, because the same current is flowing in P1 as well as P2. Look here, see, if I have the same current I, that also means it is because of the constant VGS, and that VGS is constant and the same VGS is being applied here also, and that means whatever the voltage that was applied over here, the same voltage is being applied here also, and because of the same voltage being applied over here, whatever the current was generated over here, the same current will be replicated over here. So that means the entire current will be mirrored over here. Or sometimes if I want to generate different currents of different values, I can be using the same circuit and I call that as a current source. Like for example, if I want to generate 10 millivolt, 10 milliampere of current over here, then use a current source of 10 milliampere over here, which means a constant current of 10 milliampere will be flowing over here, and that will be replicated on this P2, and I will be able to generate the constant current of 10 milliampere. So this is how we can make use of this circuit as a current mirror or current source. Now this entire setup we are going to use it over here, And since what was the agenda that we looked upon when we connected a resistive load? Look, when we use a resistive load, what was the main agenda? The current should be constant. And what was the agenda when we connected the PMOS diode connected load? Even in the PMOS diode connected load, the current was constant. Why the current was constant? Because diode connected load always ensures that the device is in saturation region, and in saturation region the current will be constant. So, in whatever load I am going to choose, the prime agenda is the load current, or the current through the load is to be maintained as a constant, and no matter what circuitry you use. We started with the resistive load, we done with the PMOS connected diode format load, and now we are looking into this. Now, only the advantage is the rigidity and the stabilized current whatever we are going to get in the load section. Here the current is more stable as compared to resistive load, and here when I use the current mirror or current source, the current will be even more stable, and the current will be we are going to have a controllable current when we go with the different loads. So, we want to try to reproduce this kind of circuit, that is current mirror. Here I am going to just copy paste it over here, that can be done, and then just mirror it, and then yes, join these two sections, left click and come over here, right click, and then left click, right click over here, and then again without clicking anywhere, come here, right click, because VDD is common to both these MOSFETs. And since I can see here, I have of course given two grounds, but I can connect the same portion over here. So, I can do this, left click, come over here, right click, again without clicking anywhere, come here, right click. So, the common ground is maintained. So, these two here, left click, right click, and again right click. So, this should be in the diode connected form, and no need to mention the current source over here, because we are not generating any current source of this value, whatever the value I am going to use. Rather, I am going to ensure whatever the current is flowing in this PMOS, the same current should be retained in the other PMOS. And do not try to set spice model with the different PMOSs, like do not try to give PMOS 1, PMOS 2. PMOSs are PMOSs, we are not supposed to mention with the different names. The simulator will understand this is one different PMOS and this is different PMOS. How it is going to understand? You can see if I just double click on this and say more, as you can see this is PMOS at the rate 0, right, and if I double click on this and say more, this will be PMOS at the rate 1. So, definitely internally they are renamed as a different entity only, and we are not supposed to rename them as PMOS 1 and PMOS 2. And I will create the export for VDD. Let us do that, and then create the export for the ground as well, and then create the export for the input, which we forgot to do that, and mention the appropriate characteristics, and then we'll do this also, output, and we have already this spice code, and we have already seen what exactly this third statement mean. They indicate the nature of the input. Let us try to simulate it, save it, and before doing that, check hierarchically the DRCs, and since there are no warnings or error, as you can see over here, let us say I will do it once again, DRC, 0 errors found, perfect. So, go to simulation, write spice deck, it will open the LT spice, remove this include none, remove option no mode page, whatever the thing you have, save it, run it, it will open this window, add plot plane, enlarge this window, add a trace, input is a sinusoidal waveform of 820 millivolt as a peak voltage, output is an inverted version with an amplified value of 4.9940 volt. So, that is how you can perform even the common source amplification using a different set of load. So, this is one kind of load that we were supposed to utilize using the current mirror circuit. So, next section will be to perform the layout operation on this, and I request all the students to perform the layout on the simulated schematic of the common source amplifier with current mirror. So, I request everyone to perform the layout on this common source circuit, wherein it is also non synchronous circuit, and it is also not going to follow any Euler's method or Euler's graph. So, the connection should be made the way how it is going to look, and of course, this section will remain same thing the way what we have done in the layout section of the earlier common source amplifier. See, if I can just show you this section is of course the same, this section is also same. Only thing is you need to eliminate this section, and or else I can just will just try it out. So, what we will do is I will just create a one more cell by the name common source amplifier current mirror layout. Oops. Then choose layout, say OK, and then I am going to copy paste this entire section because I can utilize this entire portion. Yes, I will paste it, Control 0 or Control 7 to make it suitable to fit into my window. PMOS is there, of course VDD is not mentioned, Control E, VDD, power, done, Control E, GND, ground, it is also done. Let us run small DRC check. There are no warnings because I cannot see any messages on my screen. See, 0 errors and 0 warnings. I will enlarge it, and I do not require this extension, so I will delete it. I will delete it. I will delete it. Even I delete this, I will delete this as well. Let it go. Let it go. Fine. Yeah, we will try to add it afresh. Yes. Once again, let us try to run DRC, no errors. Fine. So, now what exactly we require here, this portion is done, now I require this portion. So, this portion can be constructed how? I need to again place one more PMOS, and this I need to be connected in the diode connected form. So, I have already a PMOS. So, let us take this entire thing and I'll Control C and Control V, I will place it, no issues. And this VDD portion I will delete it for time being, because I can connect this entire same portion to this VDD. So, what I will do is I will just enlarge this X size from 30 to 50. Yes. So, it can be enlarged even more. I will make it 100 exactly. So, you bring it, let me try to reduce it to a little bit. Fine. So, I need to be connecting this portion also over here, I will do that. Fine. So, this is again a PMOS, right, and what is that I should have now? Look here, what was, yeah. So, I need to be joining the gate and the drain. So, I will do that here, the gate and the drain I can join it this way. So, and the gates are joined over here. So, I will just join, left click, come over here, right click, let us join, left click, come over here, right click, come over here, right click, joined, and you are given the input over here, right. So, Control E, input, input, input is done, and similar action I should be doing with respect to ground, because ground is here also. So, I will just extend this X size to 97, yes, and place it, and done, and we are supposed to eliminate this because I do not require this portion, because only I require this PMOS. So, this is not required actually speaking. Oh, or else this is required, because this is where how you connect both the wells. No, this is not required. So before eliminating, let me try to delete all these things, and then because I only require this only one PMOS, and look at how exactly it is connected. This portion is connected to ground. So the point of intersection between the gate and the drain is connected to ground. This portion is connected to ground. Yes. So this is how exactly your circuit looks. Now if I just run DRC, there are only 2 errors, which is fantastic. The only thing it is asking is to the minimum height error or the width error. So this is not acceptable. So it is telling don't give that much length. So I can short it down and then keep doing the DRCs. Fine. Let's try to simulate it. Let's try to understand what exactly is the outcome. I will give the output here. This is only for the understanding purpose, because as and when the circuit becomes more and more complex, the layout also becomes more complex, and I have already modeled everything. Input is here, output is over here, VDD, ground, everything is here. Now let's try to simulate it. So let's try to simulate. I have copy pasted the same spice code, and fine, it is acceptable to have a minimum DRC error, because up to 5 errors or 3 to 4 errors are acceptable. Then the only reason is this width is too large, it is telling. So I can make it close together. I mean, I can inch them close so that this error will be eliminated, but nevertheless we can simulate it. So let's go to tool, simulation, write spice stack, and everything is coming perfectly. Remove this, and again you can see there is generation of the 3. Yes, now you can see, can you just see over here what is the advantage of using this common source amplifier with current mirror as a load? The advantage is that in your common source amplifier with the diode connected load, we could sense 3 different parasitic capacitance, but whereas here we are getting only 2 parasitic capacitances, which is really a advantage, because the more parasitic capacitance, more will be the power consumption. See, I can calculate the power consumption here by adding this C1 and C2, and how can I calculate the power consumption? P is equal to, so I can calculate the power as V square, and I have the capacitances, and then I square the voltage, that is my VDD, and that is how I am going to get the power. So this is how I am going to obtain different operations and values of the common source amplifier. And of course I can see the waveforms, they are very neatly coming. As you can see over here, I can just add a trace V in, then I will add trace one more, sorry, I will plot pane, I trace V out, there it is. As you can see, this is my green is my input and the blue is my output. It is an amplified version, and I can say it's perfectly coming. So this is how I can perform the layout on the common source amplifier with the current mirror as the load. So this is what we are supposed to do in this lab, and we'll try to continue with the next lab, which we'll do with the common drain amplifier, and till then you can just practice the common source amplifier what we have done. So thank you for the patience listening. Thank you.